Hi, here we are discussing about a project extending boundary scan to perform a memory built-in self-test method. So in modern system-on-chip design, embedded memories occupy a very large part of the chip area because the memories are more sensitive part of the chip and are more likely to have a manufacturing defect compared to the logic circuit. Even a single memory fault can cause a system to crash, especially in critical applications such as automotive, electronics and networking and medical imaging. This is why the memory testings always have higher priority than other part of the chip. Okay, so here the built-in self-test BIST is a popular method used to test memories known as a MBIST because it allows the chip to test itself without depending on expensive external testers. However, the conventional MBIST adds an extra hardware, increases the silicon area and reduces the design flexibility once the chip is manufactured. Okay, at the same time, the almost every SoC already included a JTAG, which means a 1149 IEEE standard boundary scan machines for testing and debugging at the chip and board level systems. Okay, so normally this JTAG is used for checking interconnections and logic blocks, but infrastructures can also be reused for memory testing. So this is important because it avoids adding a separate MBIST controllers and instead uses the inbuilt JTAG registers for test controls and data compressions. By integrating the memory testings into this JTAG, we reduce the hardware overhead. Simply this designs and it makes test procedure more flexible and programmable. So this approach also allows the use of standard test algorithms such as a MATC and MATS plus and MATS plus plus, which can be applied in both single bit and 32-bit word oriented mode. The novelty of this work is that provide a scalable JTAG 32-bit memory test architectures that unifies the test algorithms under the boundary scan framework. The proposed method achieves a balance between fault coverages and test time and hardware cost. It has been implemented in Verilog HDLs and validated on Xilinx Vivado FPGA, where the results area, power and latency confirms that the solutions is practical and the efficient for SoC-level memory testings. Now we can verify the paper. So this paper is fully designed for the MBIST method with the extending boundary scan to perform a JTAG operations. Okay, so here JTAG means it's a joint text action group, so it will be using for testing and debugging the SoC operations. Okay, so here the basic architecture of this JTAG, first of all we need to verify it. Okay, so it's having a tap controller. So tap means a test access port. Okay, so here we discuss about the debugging process and boundary scan process which using this JTAG operations. Okay, so here the main concept, this is the architectures for this JTAG. Okay, so it's having a supporting pins of TMS and T clock, TDI, TDO and TRST. Okay, so this is the operations for this input output configurations. Okay, so here TDI means it's a test data input and TDO means it's a test data output and T clock is a test clock and TMS is a test mode select and TRST equal to test reset. Okay, so TDI means it's using for the serial data transfer debugger to target method. Okay, and TDO means serial data from target to debugger. Okay, so here this JTAG is mostly used for to bypassing the data from PC to FPGA controllers or FPGA to PC controllers, so to sharing the memory data. Okay, so here this is the architectures. Okay, so if we are given a TDI, it will be bypassing to this shift register. Okay, and again it will be bypassing to this output shift registers and again it will be come to the TDO. So this is a major operations of this JTAG method. Okay, so in between it's having a tap controllers and registers and BMT memories. Okay, so this proposed architectures will reproducing this JTAG method with the MBIST operations. Okay, so that will be given in this paper. Okay, extending boundary scan to perform a memory built-in self-test using JTAG operations. Okay, so this figure 1, the block diagram of BMT scan. So it's a basic architecture for single port memory operations. Okay, so here the TDI is the input and TDO is the output. Okay, this BMT registers, it's just bypassing the data to TDI to TDO. Okay, so in between we have a BMT controller, that is a tap controller. So it will be holding the data into the memory, and it will be testing the data. After that it will bypassing the data to the TDO. Okay, so here the first of all the TDI, it will receive the data and load the data into this BMT registers. Okay, so it's a 32-bit data. Okay, so the complete 32-bit data, once it will be stored. Okay, so and then it will initiate the data to writing operation, that is a MBIST write enable, to write the data, and it will read the data again. Okay, and then it will test the data. Okay, so with support of this BMT controller, will test the data. Okay, test means it's a comparing the data. If it is match, okay, it will be same data, means the error will not occur, so we can ready to bypass the data to the TDO. Okay, so if error happen, okay, so we need to mention this data, it's occur a error, so that's why we create a fault signal to the TDO. Okay, so here the first set of the data, it will be loading in the first set of the TMS and T clock period. Okay, so the next set of the clock, once we generated, at the time only the data it will be bypassing to the TDO. Okay, so in between we have operations of this match test algorithms. Okay, so here the match element and memory operations, it will be occur. Okay, so here the match test operations, it will come with a 4 different test operations. Okay, so which one is the first test operation is R0 to W1, R1 to W0, R0 to W1 and R1 to W0. Okay, so which means, okay, so first of all we need to read the data and we need to write the data. Okay, so you can verify this match C fault direction architectures. Okay, so here the initial we load the data here. Okay, so 1010. So once we write the data into the temporary registers of 1010. Okay, and then we write the data again into this 0101 and read the data again 0101, and again we write the data here 0101, and again we read the data here 0101. So again we write the data. Okay, so this operations continuously repeated for 4 times. Okay, and then we finally testing these operations R0 and R1. Okay, so here the comparison happen. Okay, at the time of error occur in the fault bit. Okay, so we need to detect the fault bit. Okay, so otherwise we generated the same output to the TDO. Okay, so this is a match C test algorithms. Okay, but we remodified this architectures as proposed with MATS and MATS++ architectures. So here you can verify this is a MATS+ architectures. It's having a 1 writing and 1 reading operations. It's a simple design to debugging the test algorithms. Okay, with a less number of hardware. Okay, so in MATS++, it's having a little high compared to the MATS+, but compared to the MATS C algorithms, its number of writing and reading operations, it will be very less. Okay, so here it's come with a 2 writing and 2 reading operations. Okay, so this is the only difference between this MATS C and MATS+ and MATS++ method. Okay, so every operations, it will be comes under writing and reading the data, but each operations we need to compare. Okay, so where it will be compared, so that is the main target of this testing method. Okay, so this testing method will given a priority to this BMT scan. Okay, and once we write the data into this SRAMs and we read the data and we need to test it the data into this BMT controller, and it's also initiate the address counter to increment the address, and also it will controlling the reset part, T clock and the other bits, the fault bit. Okay, and instruction register SO, everything we need to write a code in BMT controllers. Okay, so with support of the Verilog HDLs. Okay, and this is a single port SRAM memory. Okay, and the dual port configurations also it will be given here. Okay, So here this one is a dual port configurations. Here they are using for two set of the memories. Okay, so here the first BMT registers, it will bypassing the data to the second BMT registers. Once we tested the same sequence repeatedly again, after that we need to send the data to the TDO. Okay, but this dual operation based testings, it will be more secure, higher accuracy operations, but it will take a more time to deliver the output in TDO, and also it will take for more SRAM operations. Okay, so here this work we have developed in Verilog HDLs, and we synthesized this code in Xilinx Vivado, and the testing part we analyzed in modellisms. Okay, so now we can verify the coding part. Okay, so this is a initial coding, single SRAM architectures based MBIST algorithms. Okay, and here initially we need to design a debugger model. Okay, as per this debugger model we can create this T clock, TDI and TDO based signals. As per that we can generate this BMT scan single SRAM match algorithms. Okay, here we have included the single port memory and address counters and BMT scan operations. Okay, the same way we are modified the code in BMT scans MATS plus algorithms and the MATS plus algorithms. Okay, and the same method we have included the MATC multi SRAMs architectures and MATS plus multi SRAM architectures and MATS plus multi SRAMs architectures. Okay, so here this part of the simulations, it will be included in modellisms. Okay, so here you can verify that the start signals once came. Okay, so we initiate the data to the input. Okay, so here this is a debugger model generations. Okay, so here this is a T clock and this is a TMS part and this is a TDI part. Okay, so data, clock and the level signal. Okay, so here it will be shifting the data. So in the debugger model we receive this data parallelly from the TDO. Here this one is a TDO output. Okay, so we shifted again this TDO on the test bench model, and finally we compare the data. So if it is match or not. Okay, so if it is match, we given an error equal to 0, otherwise we generate an error equal to 1. Okay, so here this is a single port RAM memory. Okay, so here you can verify it. So this is the first set of the data. Okay, so once it will be loaded into the BMT registers, and after testings it will generate output in the next cycle of the TDO. Okay, so this is the input and this is the output. Okay, the same signals it will be present here. Okay, so how much times you can run, you will get a same output. Okay, so here we can give any value and we will receive the value in the next cycle. Okay, so this is the first cycle of the data and this is the output cycle, that is the next cycle of the data. Okay, so here initially we load the data into the BMT registers. Okay, so here this one is an input, this is the input top model. Okay, so this is a single port SRAMs, address counter and BMT scan method. Okay, and BMT registers. Okay, so here the scan input, it will be received here. Okay, and it will shifting the output with support of the shift registers. Okay, so this is the shifting output one by one. So here it will be shifting. Okay, so once the shifting process finished, okay, so we can take control in the BMT controller. Okay, so here the BMT controller will take a control operations. Okay, so here we need to write 4 times. Okay, so why? Because in the paper they will be writing for R1 registers, R2 registers, R3 registers, R4 registers. We need to read, write and process repeatedly 4 times we need to do. Okay, so here that's why the MBIST write enable will be generated for 4 times. Okay, at the times we write and read the data from R0 registers, R1 registers, R2 registers, R3 registers and R4 registers. Okay, and then finally we compare the value. Okay, so R0 and R4 value we need to compare it. Okay, so once it will be match. Okay, so we generate a fault bit equal to 0. Okay, So this is a fault flag equal to 0, and we initiated to the initial state, and also we initiated data to transfer with support of this shift BR and clock DR signals. Okay, with support of these two signals, the BMT registers will generate a output in the second period. Okay, so here this one is the second period. Okay, so here the BMT registers, it's working as a parallel mode. Okay, so here at the time of data shifting to the output, okay, so it's also receiving the input from the scan-in. Okay, so now it's ready for the second test sequence. Okay, the same method we followed for the MAT-test plus algorithms. This one is a MAT-test plus algorithms. Here we are used only the 1 registers. Okay, so R0 registers only we are used. Okay, so this one R0 and R1, 2 registers we are used for testing. Okay, and MAT-test plus plus, okay, so we used for 3 registers. Okay, R0, R1 and R2. Okay, the same method will be handled. Okay, so here 2 writing operations and 2 reading operations. Okay, as per that we control the MBIST method. Okay, and this one is a multi-port operations, the next one. Okay, so here this one is a multi-port operations. So multi-port operations means, so we need to transfer the data from first BMT register to second BMT registers. Okay, so and then we can possible to give an output to the TDO. Okay, so this is a TDO. Okay, so it will be taken 1 cycle delay. Okay, this is the first cycle and this is the second cycle. So second cycles it will be reading happen in the BMT 2 registers. Okay, and third cycle only will get a data. Okay, so that's why it will be taken some delay. Okay, at the time of these operations, we initiate the shift DR to BMT register mode. Okay, so that's why it will be create this output. That's why it will create this output. Okay, and it will produce the error signal also for testing method. Okay, so after that the TDO it will be come with the same output. Okay, that's why the error goes to low continuously. Okay, so this is a multi-port operations. Okay, so here we used a dual SRAM architectures in the architectures. Okay, so this is for the next one. Okay, so here this one is a MAT-test plus plus method. Okay, so this all the models we have synthesized in Vivado, Xilinx ATIC7 FPGA. Okay, and we compared all the parameters in terms of LUT, flip-flops and occupied slices and power and delay. Okay, so these are the folders for testings we have used. Okay, so MAT-C and MAT-test plus and MAT-test plus plus for multi-port operations, and this is for single port operations. Okay, and this is a Vivado results. Okay, so here this one is a single SRAM architectures. Okay, so here you can analyze the parameters. LUT equal to 2768, flip-flop equal to 8522, and summary equal to 0.168, and delay equal to 2.385, and this is the RL schematic. Okay, so this LUT size it will be depends upon the memory size. Okay, so here we are used for 32 cross 256 size. Here we initiate the initial thing is TDI, TMS, T clock and reset, and NTR reset and clock, and this is address counters. It will be generating the address depends upon this increment address. Okay, and this is a single port RAM. Okay, and this is a BMT scan. Okay, so single port RAMs come with unique architectures designed for Verilog HDL. Okay, so it's not generated with any core. Okay, and this is a BMT scan method. So it's having BMT registers and BMT controller. Okay, so this BMT registers it's purely designed with a shift register method. Okay, with a multiplexer. Okay, and this is a BMT controller. Okay, so this same design we have developed in a multi-port method with the 2 memories. Okay, and here it will be occupied with 2802 and 8600 flip-flops. Okay, and this is a schematic. Okay, so here also same address counter, but here we used for two single port SRAM architectures with the BMT scan. Okay, so this BMT scans have two BMT registers. Okay, BMT register 1 and register 2. Okay, so this is a BMT control dual memory controller. Okay, so this one until schematic. Okay, so this part we have compared. So this is a comparisons report. So March C, March C dual memory, and MATS and MATS plus dual memory, and MATS plus plus and MATS plus plus dual memory, and we have written abstract document for this project. Here this is abstract, the title. Okay, so objective of this work, problem statement. Okay, and related notes, the existing and proposed method with the March and MATS plus plus architectures and architecture descriptions with the literature survey and related notes. Okay, so as per the VLSI design. Okay, and finally come up with the references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.